Okay, so I have now seen one way of getting new strings from my original string, and the family of new string has the repetition of the b squares and d squares with me. Now I would want to formalize this result for any grammar. For that, let us see what is happening inside this grammar. So let us denote by t the length of the longest production. Okay, if I had 10 productions in total with me, and the longest production has the length 3, it could either be S producing the string of variables ABE, or S producing the string of variables BDB, or B producing this mixed string BSD. So I could have chosen any production and would have said, okay, this is the longest production. So if I say that, okay, T is the longest production in my grammar, okay, now I'm going to give you a result, which is the link between the height of the tree and the length of the yielding of that tree, or in other words, the length of the string produced by that tree. So there is a result, there is a relationship between these two quantities, the height of the tree and the length of the string produced by that tree. So consider this diagram. Suppose I have some grammar, and the maximum length of any production of that grammar is t. So I have just look at this thing. If I say that the height of the parse tree of some grammar is 1, if I just simply say this thing, that the height of parse tree of some string of that grammar is 1. So all you would say is that the maximum length of that string can be t. It cannot be greater than t. The reason is, if somebody says that, okay, the height of some parse tree is 1, it means that, okay, I am simply using one of the productions from my grammar, and that production has only the string of terminals in it. So I have denoted by t the length of the maximum production. So now I say that if the height of the parse tree is 1, the length of the string produced by that tree is maximum is at the most t. And now if somebody says that, okay, what happens when the height of the tree is 2, then you would say, well, the length of the string produced by that tree is t square maximum. You're just giving me the upper bound. And if somebody says that, okay, the length of the parse tree is I, then the upper bound for the length of the string produced by that tree is going to be t top I, or t to the power I. And similarly, if the height of the tree is r, then the upper bound on the length of the string is t top r. So if somebody says that, okay, maximum height of the tree is r, then the maximum length of the string is t top r. So that is the relationship between the two, and we can always talk about it in the reverse manner as well. And so how do we talk about in the reverse manner? So first of all, I'm restating my result, that the height of the parse tree is r, then the upper bound on the length of the string produced is t top r. Now the reverse of this result would be, or the converse of this result would be would be that if there is a tree if there is a string whose length is greater than tr, then I am sure that the height of the parse tree for that string is bounded below by r plus 1. Why? Because if the height of the tree is r, then the length of the string is bounded above by tr. Now I have got a string whose length is greater than tr. It means that the height of the parse tree is at least r plus 1. It can be more, but it is going to be at least r plus 1. So I'm going to play the pumping lemma, I should rather say. The pumping lemma plays on this idea that this is going to be this is the very important number in reference to the pumping lemma. If you guys remember from the pumping lemma of the regular languages, I always talked about the pumping of a string whose length is greater than some number. and we called that number as the pumping constant. So there is a question. No, Marceline, you don't do it now. You just do it when I ask you to do it. It appears you were not there in the first session. Don't be in a haste, please. And it is for everybody as well. Don't be in a haste. Don't write your attendance right now. Uh, so if you remember from the pumping lemma of the regular languages, there was some constant. And if the length of the string was greater than that constant, we would say, okay, that is the string which is sufficiently long. So this number T top R, this is going to serve as the pumping constant. I have told you guys about T, that T is the length. Yeah, T is the maximum length. Yeah, T is the length of the longest production. But I have not told you anything about the R. Now R in this case, I'm guys telling you right now that R is the number of variables in the grammar. So whenever I give you some grammar, you would know how many variables it has, R, denoted by R. You would know the length of the longest production, denoted by T. So these are the two quantities that you can always get from the context-free grammar. And then you would say, if there is a string whose length is greater than this tr, you are bound to be sure that, okay, that string is pumpable. How is that pumpable? I'm going to show you guys later. But that tr is known as the pumping constant. In the case of the context, in the case of the regular languages, it was the number of states of the minimal DFA. And the pumping constant in case of the context-free grammars is T top R, where T is the length of the longest production, R is the total number of variables in that thing. Now I have got this intermediate result with me, and that intermediate result says that whenever the length of a tree is greater than this number, whenever the length of some string is greater than this number, then rest assured that the height of the parse tree for that string is going to be at least r plus 1. It could be r plus 2, it could be r plus 3, but it is bounded below by r plus 1. Okay. So when I say that the height of some tree is r plus 1, it would mean that I have r plus 2 nodes along the longest path. And if there is, I hope that you guys have idea about the height of the tree. Uh, Binary trees, I think you guys have studied the binary trees, isn't it? You guys have the idea
Yes,
how?
yes.
Okay, great. Thank you very much. Thank you very much. So when I say that the height of the tree is r plus 1, it means that number of nodes along the longest path are r plus 2. One thing is for sure, that the last node is going to be a leaf. So if it is a leaf, it means that this is a terminal symbol. So out of r plus 2 nodes, r plus 1 nodes have the label as the variables, and only the last node has the variable as the terminals, label as the terminal. Now look at this longest path. This longest path has r plus 1 variables in it. Fine, if it has r plus 1 variables in it. And how many variables do I have? In total, I have got r variables. Now I have got r variables with me, and there are r plus 1 places in which have to be filled by the r variables. The pigeonhole principle says that you have a repetition of some variable. It is bound to have a repetition of that variable. Now this happens to be one of the very interesting results, as we had the interesting result previously during the proof of the pumping lemma for regular languages. So this is an interesting result in the proof of the pumping lemma for context-free languages, that there is a repetition of that variable h, which is coming, or which is motivated by the pigeonhole principle. So the thing is, I have got r plus 1 places which are supposed to be filled by by variables, and in total there are r variables. So I'm bound to have a repetition of some variable. Let us call that repeated variable as to be the h. Now I'm just going to impose one more condition on it, and that one more condition is that I'm going to select this variable h in such a way. I mean, it is not necessary that only one variable repeats. There can be repetition of many variables, because the pigeonhole principle says that if there are if there are less pigeons, then if there are less pigeonholes as compared to the pigeons, then I would have at least one pigeonhole that would have more than one pigeons in it. So that would simply say that, okay, I'm going to have repetition of at least one variable. There is a possibility that there are repetitions of more than one variable. That is also okay. Now the thing is, I'm going to consider for the middle subtree, I'm going to consider that variable which appears only once. Now we call it as, okay, we call it in this way, that repeated variable is the deepest variable. It means that I am deliberately going to pick a subtree from the derivation tree in a manner that age is the only variable that appears during along that path. So that is how we say that, okay, this is the deepest substring in this, sorry, the deepest variable in that parse tree. I hope that this point is clear. If this point is clear, then I will move forward. Rather, I should ask this question. If this point is not clear to somebody, please ask me now.
Sir, take age to be deepest, ये concept please दोबारा बता दें, समझ नहीं आया deepest का क्या मतलब है यहाँ पे?
Okay, but deepest in the sense that if you look at the if you now see, what do I mean by deepest? If you look at the derivation tree or the derivation structure of a string, you always start from the start variable. So the start variable means that the length of the sentential form is 1, and when you move forward in the derivation, the length of the sentential form always keeps on increasing. And when the derivation ends, you have all of the terminals, with you. Now along the way, the number of the variables is going to increase. It is going to reach at its maximum value, at maximum length, and then the number of variables are going to reduce as soon as you reach at the at the terminals or the endpoints. Now that particular apex wherein you have the maximum number of the variables available with you, that is somewhere we call as the deepest level. Now if you are interested in looking at the repetition of some variable, now please proceed from that point onward, that you have repetition of only one variable available with you during that search for the repeated variable. I hope that makes some sense.
जी sir, ठीक.
Okay, great. Okay, now that is great. So now I know what type of repetition of the variables I'm going to study. I mean, look at this way. Uh, if somebody says that I am looking at the repetition of some variable, but during the repetition of that variable, they create a middle tree, and along that middle tree, there is a repetition of another variable. Now that selection of the middle subtree is not good, because I am having another repetition of some variable. So by deepest, I also mean that I am selecting a subtree such that there is repetition of only one variable. Okay. So the thing is, I have some string W whose length is greater than tr, and I'm sure the height of the parsing tree of that string is going to be at least r+1. And pigeonhole principle says that one of the variables is bound to be repeated. Then I say I am going to select that variable or repetition of that variable, which is the deepest one. So I have this structure with me, which I have already discussed with you guys, and that structure is okay. No. I'm going to one more thing. Well, I have now a middle tree, an outer tree, and the inner tree. Okay. Now this structure is going to help me out in dividing my original string into 5 substrings. Okay, yeah, 5 substrings: U, V, X, Y, and Z. Remember that a sufficiently long string is going to give me 3 sentential forms and 3 substrings. So in the terminology of the outer subtree, the middle subtree, and the inner subtree, and also the terminology of the sentential forms, I would have the variable s from the outer subtree, the variable s giving me the sentential form, UHZ, and then the sentential form in the middle subtree is going to be H giving VHY, and then the sentential form coming from the inner subtree is going to be H yielding X. Okay, so this is what I have explained to you guys earlier. And look at this thing. S yielding UHZ. So H is a variable. It is bounded. It is bound to be replaced till the time I have got all of the terminals with me. So there are two possibilities. Either H is replaced by VHY, or this H is replaced by the substring X. Uh, if I repeat it by H replacing VHY, I would have one copy of V and Y. And if I use it again, I would have two copies of V's and Y's. And if I repeat it the third time, I would have three copies of V's and Y's. And finally, I have to terminate my derivation. So I would be replacing H by X somewhere whenever I desire to end the derivation. So that would mean I am able to create a new string of longer length with UVIXYIZ. So the same number of copies of V and the same number of copies of Y. Remember, we did the same story in the pumping lemma for the regular languages. We said that, okay, we are going to divide our string into three substrings, X, Y, and Z, and I can have the repetition of as many copies of Y as I may please. So in the case of the pumping lemma for the context-free languages, I have the decomposition of my original string into five substrings U, V, X, Y, and Z, and then I can have repetition of as many copies of V as I may please, with the condition that the same number of copies of Y are also going to be pumped in. So that is the story of the pumping lemma for the context free languages. Let's see if I have formalized it as well. But if I compare it, if I try to compare it with my original CFD on the very first slide, I would say that my original string A square, B square, C square, D square, E square, when it is decomposed into five substrings, then the A square is the substring U, B square is the substring V, C square is the substring X, D square is the substring Y, and E square is the substring substring Z. And I can have when it comes to the comparison of the sentential forms, I would have S replacing A square, B E square, referring to S replacing UHZ, B producing B square, B D square, as a corresponding to H producing VHY, and B producing C square corresponds to H producing X. So that is the analogy between the general form of the pumping lemma and comparison with the original grammar that I have discussed earlier. Yeah, that is how we are going to write it in another way as well, only in terms of the sentential forms. So this is just the structure in wherein we can see, okay, why the number of copies of Y, V and Y are increasing, because every time there is a replacement for H, we have got two possibilities: either go for VHY or go for X. If you go for VHY, you have once again a possibility for the replacement of H. If you repeat this thing again, you have got two copies of Y and two copies of V and two copies of Y. If somebody has no clarity up to this point, please ask me a question. Otherwise, I'm going to proceed forward. Okay, great. So uh, the thing so far is that if the length of some string is greater than dr, that string can be decomposed into five substrings, and in those five substrings you will find two substrings V and Y that can be pumped in as many times as you may please, but with the constraint that there would be as many copies of V as there are copies of Y. Okay. And there was one observation in the decomposition of a sufficiently long string in pumping lemma for the regular languages. it was about y being not an empty string, and there was a constraint on the length of the substring xy. So I have got some constraints over here as well. There is some condition on v and y, and there is some condition on the substring vxy whenever I'm going to divide my string into 5 substrings. Okay. The first observation. The first observation is that v and y, they cannot both be empty. One of them can be empty, but both of them cannot be empty. Okay. I tell you the reason. Okay. Yeah. Remember, I said that whenever you are given a grammar, always remove the epsilon productions. Gone. And then always remove the unit productions. Gone. So once the epsilon productions and the unit productions are removed, and I am doing something in the sentential forms, so at each level of production, at each level of substitution, the length of the sentential form is always going to increase. I repeat myself. Whenever you are performing a substitution in a sentential form, the length of the sentential form is always going to increase. The reason is, the reason is I do not have any unit production, and I do not have any epsilon production. So when I say that the H yields VHY, so the length of this sentential form is supposed to be greater than the length of the H itself. So that would mean that if I remove H from this, I would have some condition on V and Y, and that some conditions is that, okay, both of the V's and Y's cannot be empty. So that was the reason, one condition on V and Y. And then there is another condition. And that other condition is the substring Vxy when combined together is supposed to be bounded above by tr plus 1. Okay. Now, why is that condition important? Remember, I said that the variable h is at the deepest level. So it is the only variable that repeats itself. And let me get back to my some result that I have discussed before. I have a tree. In that tree, there is a repetition of the variable, some variable. Now, it would mean that the height of that tree cannot be greater than r plus 1. It is supposed to be r plus 1 because I am making sure that only one variable is repeated. If only one variable is repeated, that means that the height of the tree is r plus 1. And if the height of the tree is r plus 1 at the most, it means that it imposes, rather it poses a condition on the length of its yielding, and the length of that yielding is going to be vxy. So that sorry, the yielding is vxy, and the length of that yielding is supposed to be bounded above by tr plus 1. Okay. If this point is not clear, please ask me a question, otherwise I move forward. Okay, so with these two conditions, I have the formal statement for the pumping lemma of the for the context-free languages. Uh, if there is an infinite context-free language L, then there is some integer P. We call it as the pumping constant. And whenever, if you choose a sufficiently longer string W, we are always able to decompose into 5 substrings U, V, X, Y, and Z, with the condition that Vxy is bounded above by P and V and Y together are not empty, and that this new substring is once again in the language. As a matter of fact, I have a family of the substrings available with me. And since it is a necessary condition, now this means that I will be using this pumping lemma in its contrapositive form. And the contrapositive form would be that there is a string in the language which is not pumpable. So that is how we are going to do. As we did with the application of the pumping lemma for the for the regular languages, same is going to be the story with this thing. Okay. If okay, you may mark your attendance now. only 10 minutes are left, so I'm quickly going to discuss one of the example of the pumping lemma for the context-free languages. Okay, application. Yeah, take the example. Uh, I think last week I just told you guys that the string, no, the language A and B and C n is not context free. So today we are going to prove that this language is not context free. The intuitive reasoning that this language cannot be context free is that we have one DFA, sorry, we have a PDA, and that PDA has only one stack. That PDA stores the incoming A's and then matches them with the incoming B's. Once the number of A's and the number of B's are equal, the machine would have no storage of A's available with it, and all of the B's on the input tape would have been exhausted. Only C's are left. Now the PDA has no mechanism of verifying that the number of C's on the input tape was indeed same as the number of A's or the number of B's. So that is the intuitive reasoning that this language cannot be context free. But now let us apply the pumping lemma over it and say that, okay, why it is not context free. Once again, I am going to suppose on the contrary, that this language is context free. As a matter of fact, I have to show that this language is not context free. I'm doing the proof by contradiction, so I'm supposing that this language is context free. So if this language is context free, so it would mean that every sufficiently longer string is pumpable. Okay, so then I said, okay, let P be that pumping constant. And if P is that pumping constant of the language A and B and C n, then consider this new string that I have constructed, A P B P C P. This is the new string that I have chosen from the language, and I'm saying that this string is in the language. Well, this string is bound to be in the language because it has the same number of A's, the same number of B's, and the same number of C's. One thing, and the second thing is that they are all in the same order. Train of A's followed by train of B's, and then followed by train of C's. So it is not mixed ordering. Okay. Now, I know I have supposed that the language is context free. So I am able to decompose my string into 5 substrings, U, V, X, Y, and Z, with the condition that Vxy is less than P and Vy is greater than or equal to 1. So there would be multiple possibilities. Now, what are multiple possibilities? Well, those multiple possibilities, since just remember that there is a condition on Vxy being bounded above by P, length of Vxy bounded above by P. So one way is when I say that Vxy is in the first train of A's. Can somebody tell me what sort of contradiction I'm going to arrive at later? Are you guys following me? Somebody?
Yes, sir.
Okay, so my question is, can somebody tell me if what sort of contradiction I'm going to arrive at later?
सर थोड़ा सा लास्ट का रिपीट कर दें प्लीज.
हाँ, वो मैं रिपीट कर देता हूँ. देखिए, I said that I'm bound to have this constraint that the length of Vxy is bounded above by P. So I'm considering various cases, and the first case is that the Vxy substring is completely contained in the train of A's, as is shown in this diagram. So I would have V consisting of some A's, X consisting of some A's, and Y consisting of some A's. But can somebody tell me what sort of contradiction I'm going to?
सर इसमें अगर हम V और
सर
Y
V
को रिपीट
X
करेंगे
Y
तो
की
P
लेंथ P से ज्यादा हो जाएगी. That should be the
No.
contradiction.
Somebody else was also talking. No, but not that way. The lady, yeah.
सर यही था कि अगर हम v और y को रिपीट करेंगे तो a ज्यादा हो जाएंगे b और c
Exactly.
से.
Yeah. Akbar, were you saying the same story or something else?
सर वी एक्स वाई को रिपीट करेंगे तो पी से लेंथ ज्यादा हो जाएगी. बहरहाल मतलब पी की जो कंस्ट्रेंट है वो ब्रेक होगी.
नहीं, वो कंस्ट्रेंट ब्रेक नहीं होगा. The other lady was correct. Who was the other lady who was giving me this answer?
Sir, Zoho.
Okay. Only less time is left. Yeah. That gave the correct answer. I am going to have more A's than the B's and the C's. So that is the contradiction I'm going to arrive at. Because when I pump in some V's and the same number of Y's, I am going to increase the number of A's. And in the new string, there would be train of A's followed by train of B's followed by train of C's. Although the number of B's is going to be equal to the number of C's, but the number of A's is going to be greater than P in both the cases. So I have distorted the structure of the string, and that string is not going to be in the language. Okay. And another thing can happen. Let me see if there is a case 2. Yeah, same is the story when I say that vxy is completely contained in the train of B's, and if I pump in now, I'm going to increase the number of B's. Okay, and if the train of vxy is contained in C's, and when I pump in, I'm going to increase the number of C's. Now, the story of the mixture can appear. That mixture could be vxy is contained in A's and B's, and yeah. But I think I'm going to share these slides with you guys, and I want you to think over it for yourself as well and see what type of contradictions you're going to get. The story is
सर ये आप भी जरा दोबारा से समझा दिएगा नेक्स्ट लेक्चर में.
no. I want you to think.
प्लीज.
No. I want you to think over it.
नंबर ऑफ सीज कम हो जाएंगे ए और बी से.
Exactly. Number of C's कम हो जाएंगे. बिल्कुल, you're right. नंबर ऑफ A's भी ठीक रहेंगे, नंबर ऑफ B's भी ठीक रहेंगे, लेकिन नंबर ऑफ C's जो है ना वो बढ़ जाएंगे. अच्छा, थोड़ी सी और भी प्रॉब्लम आ सकती है, और वो प्रॉब्लम ये आ सकती है कि आपको ये किसने कह दिया कि नंबर ऑफ A's in V is going to be the same as the number of B's in Y. ये तो जरूरी नहीं है, क्योंकि वो तो आप सब ट्री को देख रहे होते हैं ना, पार्सिंग ट्री को देख रहे होते हैं, डेरिवेशन को देख रहे होते हैं. तो ये गारंटी बिल्कुल भी नहीं होगी कि वीज में जो नंबर ऑफ एज हैं वो उतने ही होंगे जो कि वाई के नंबर ऑफ बीज होंगे. ये इस चीज की भी गारंटी नहीं है. गुड. आई थिंक दिस वाज दाऊद who said this thing.
यस सर. यस सर.
Okay, great. So there are a few other cases as well. Just think on them, and you're always going to get a contradiction. But I am interested in knowing the reason behind that contradiction. So once you have found out that one, the entire purpose of the understanding of the pumping lemma would have been served. Yeah. So any other question, please?
सर ये रिकॉर्डेड लेक्चर्स कब मिलेंगे?
यार ये रिकॉर्डेड लेक्चर आपको भी मिल जाएंगे. पहले वाले मिल गए? No. Okay. Any other question, please?